Let's continue the ZAERO Advanced Training, Section 9, the Transient Ejection Loads Analysis module. So first we'll review the background here of the ejection loads module. The transient ejection loads analysis computes the transient response of the structures due to store ejections. It allows multiple store ejections in a sequential scheduling while the aircraft is maneuvering due to the pilot's input command. The computational procedure of the transient ejection load analysis is very similar to that of the transient maneuver load analysis. And the majority of the ejection loads inputs are identical to the maneuver loads analysis, except we have the additional input for the ejection forcing functions and the change of the structural properties due to the separation of stores from the aircraft structures. Because of the structural property variation after each store ejection, the system matrices of the state space equation is time varying. These time varying system matrices are discretized into several piecewise constant system matrices forming a set of state space equations, and this discretization process is based on time intervals, which are defined by the starting and ending times of the transient response computation as well as the ejection times of the stores. Now, because of this, unlike the linear gust loads and maneuver loads analysis, whose total loads can be superimposed by the static trim loads and dynamic loads, the ejection loads analysis is nonlinear, so that the time history of the dynamic loads depends on the initial trim condition. And because the ejection loads analysis is nonlinear, only the state space approach is available. And here's the bulk data interrelationship for the transient ejection loads analysis. The ejection loads card is very similar to the maneuver loads card, except our new cards is the DFORCE bulk data card, which defines the structural grid where the ejection forces are applied. The remaining cards are the same as the maneuver loads analysis. So the two new cards here, we have the ELOADS bulk data card, which defines the aeroservoelastic system, time integration, ejection forcing function, and changes of the structural properties due to store separation for the transient ejection loads analysis. And then we have the DFORCE bulk data card, which defines the dynamic forcing function and the structural grid points where those forces are applied. So this is the ELOADS bulk data card. We have an ID number, which is referred to by the case control command. A con ID refers to the ASE controller card. Flut ID refers to the flutter card. RAA ID refers to the minstat card. The states field refers to the MLD stat. And as we mentioned, unlike the MLOADS, this is required to be, the RAA ID is required to be greater than 0 because you must perform the RFA because the state space analysis is the only analysis that is available. You cannot perform a frequency domain analysis. The states field refers to the MLD stat card for specifying airframe states. The command card refers to the MLD command card specifying the pilot input commands. The MLD time field refers to the MLD time card. The MLD print field refers to the MLD print card to allow you to specify an output file to output the time histories of parameters of interest. And then lastly, we have the open-ended input to define the ejection time of these stores and the forcing functions. So EJ time, the first field for each row, is the ejection starting time. Next, ID force is the identification number of the DFORCE card, which specifies the ejection force and the structural grid point where the force is applied. The CON-ML field refers to a CON-M list card, which specifies the change of mass due to the separation of the store. And then I'm going to skip PAN-LST and go to the del M, del C, and del K. So we have two options to specify the change of mass. You can do it through the CON-M list card, which refers to the CON-M2 cards. So if you have CON-M2 cards, which define all of the mass of the store, you can just copy those into your ZAERO input and then use the CON-ML option. The other option is to directly specify the change in the mass, damping, and stiffness matrices. So this del M, del C, and del K are matrix names, which refer to a matrix which represents the change of mass, damping, and stiffness due to the separation of the store. Now, these matrices can either be defined in the G-set or the generalized coordinates. So if they're defined in the G-set, then you would set the G-set field to be yes, and if they are in the generalized coordinates, then you would set G-set to no. So for G-set equals yes, ZAERO will internally pre and post multiply by the modal matrix to convert the G-set, del M, del C, and del K matrices to the H-set, the modal coordinates. Lastly, we have the pan-LST field. This refers to the pan-LST cards, which define the list of aerodynamic boxes of the store. So in this case, after the store is ejected, ZAERO will zero out the forces on those boxes so that those boxes no longer contribute aerodynamic force to the model. Our remarks down here, the same as the maneuver loads analysis, the ejection loads analysis must contain rigid body modes. So the support field and the assign FEM executive control command must be specified. For an asymmetric analysis, the full span model must be modeled. And then if you want the forces or component loads in your time history output, then you must import the KGH matrix. But remember, you can also import the MGG or MGH matrix, and ZAERO will compute the KGH matrix for you. The DFORCE card, which we'll talk about soon, specifies the forcing function. And the EJ time fields in the ELOADS card is the relative starting time. So if the DFORCE card defines a forcing function that starts at 0 seconds, but the EJ time is 1 second, then of course in the final analysis the actual forcing function will start at 1 second. And then we talked about the change of mass here. So let's G-set. Okay, we talked about the G-set option. Final note here for the del M, del C, and del K matrices. The units are in the FMM unit and FML unit, which are defined in the ZAERO Z bulk data card. So those are the model units, which is what you would assume because that matches the Nastran units. Okay, next is the DFORCE card. This defines the set of dynamic forcing functions at the structural grid points or on the aerodynamic boxes where the forces are applied. So we have an ID number referred to by the ELOADS card. The pan-LST field refers to the pan-LST cards, which define a list of aerodynamic boxes on which the time-dependent pressure is applied. Fact P is the magnitude of the pressure coefficient, and then ID tab P is an identification number of a table D1 specifying the pressure time function. So as an option, you can apply the forcing function as an aerodynamic force on boxes, or you can specify it as a force on grid points. So that is the open-ended input here is for applying a force on the grid points. You could also make use of both at the same time, but I think that doesn't make very much sense. Normally you choose either a pressure force or a grid force. So ID grid is the identification number of a structural finite element grid point. Comp I is the component number, which can be 1, 2, 3, 4, 5, or 6. Factor is a factor, and then ID tab is an identification number of a table D1, which specifies the forcing function time history. So you can see that one DFORCE card can actually apply a force on multiple grid points. So if you have, say, 2 attachment points for a store, and then you have explosives at both connection points that blow the store away from the wing, you can define the forcing function for each of those 2 grid points in this one DFORCE card. So let's look at an example here. This is a ZAERO standard test case, the forward swept wing. So we have 2 store ejections in sequential order of the forward swept wing during 1G cruise at Mach 0.9. velocity of 1,005 feet per second, and the given air density. The store locations, store number 1 is at this grid point, and then store number 2 is at this point. For store number 1, the ejection time is 0.1 seconds, the store mass is 18.6 slugs, and our ejection force is 0. So for this particular store, we're not forcing it away from the aircraft, we're simply going to drop it. So this is going to illustrate that the structure will respond to the sudden decrease in mass out here at the wing when we drop the store. The second store inboard, the ejection time is 1 second, the store mass is once again 18.6 slugs, and here we have an ejection force that peaks at 10,000 pounds. So in this case, we're going to blow the store away from the aircraft. So the response will be a combination of the force that's used to push the store away from the aircraft, and then also the change in mass due to the dropping of the store. So at grid point 121 is the first store, has a 0 jettison force, as we said, and at a time of 1 is grid point 111 and a peak jettison force of 10,000 pounds. And this is our forcing function here. So from 1 second to 1.1 seconds, so over a time period of 0.1 seconds, the force will ramp up from 0 to 10,000 pounds. And then the next 0.1 seconds, it'll ramp back down from 10,000 pounds to 0 pounds. And these are the bulk data cards. So our ELOADS card, we have 2 rows here representing the 2 stores. So the first store, the ejection time is 0.1 seconds. The second store, the ejection time is 1 second. For the first store, we refer to this DFORCE card 101, and it defines the store mass here. So our store mass is at grid 121, only in the Z direction. This is the force here. So the force is in the Z direction. Our factor is 1, and then our table is down here. And for this one, our forcing function is 0. So we have 0, 0, 0. So the forcing function is 0 for the first store. Meanwhile, our first store, we have the mass defined by the CONM list. So the CONM list card is here, which refers to the CONM1 card. The CONM1 card here defines our mass of 18.6 slugs. So this is our mass that will be removed when the first store is dropped. Now for the second store, that refers to the DFORCE card with ID 102. So this one, our forcing function is applied at grid 111 in the Z direction, and our forcing function is defined here by this table D1. So you can see at time 0, and remember this is relative to the EJ time, which is 1 second. Time 0, the force is 0. Time 0.1, the force peaks at 10,000 pounds, and then at time 0.2, the force drops back to 0. Meanwhile, the mass of our second store is defined by the delta M matrix, and it's defined in the G set. Our G set is set to yes. So for the second store, we're not using the CONM option, we're using directly the mass matrix option. So our mass matrix delta M is defined by the DMIG card. So for this particular mass, we're defining a mass of 18.6 slugs, but only in the Z direction. So this is at grid point 111, direction 3, which is the Z direction, and our mass of 18.6 slugs. So this mass will be subtracted when this store is ejected. This is the bulk data card interrelationship. For this test case, we have our ejection loads card refers to 3 plot time cards, so we can visualize the response, and then also output the Nastran force and moment cards for detailed stress analysis and Nastran after the fact. We have the rational function approximation defined through the min-stat card. Our flutter card defines the analysis parameters. We have the rigid body reduction card to clean up the rigid body modes. We have the MLD stat card referring to the MLD trim. So we talk about the MLD trim here. This card specifies the trim loads at 1G cruise condition. The trim solution is obtained by performing a trim analysis to satisfy the 1G cruise condition using alpha and canard as the trim variables. So this DMI card here is copied and pasted from the output of the trim analysis, and this is now in the input of our ejection loads analysis. And then our canard and alpha are also copied from the trim solution. We have the MLD time card to specify the time parameters, MLD print to output some forces of interest here through our, so we're going to measure component loads. Then we have the DFORCE card, which we've talked about on the previous slide. Cont list, DFORCE, we saw those, DMIG, we saw these cards on the previous slide. So this is the results from doing the analysis. So our measured quantities here, we have the time derivative of the airframe state alpha. We have the first elastic modal displacement response, the first elastic modal acceleration response. We have the acceleration at grid 90, stress SA1 and SB1 at C bar 110. So at 0.1 seconds, remember we're just dropping the first store with no forcing function, and then at 1 second we're dropping the second store with a forcing function. So you can see, let's move to the acceleration at grid point 90. When we drop the first store, that causes a response in the structure. And then when we drop the second store, you can see kind of a similar response due to the reduction in mass, but then we also have a large response here, which is due to the forcing function. So for the second store, the response is dominated by the forcing function. For the first store, of course, with no forcing function, the response is simply due to the sudden change in mass of the aircraft. Next, we'll look at the wing root bending moment, and we'll compare the mode displacement result and the RFA summation of force results. At time minus 2 seconds, the wing root bending moment is 4.5 times 10 to the 5 pound-foot, and that's due to the initial trim load, so that's constant until a time of 0.1 seconds when we drop the first store. And we can see the response of the wing root bending moment, and then at time 1 second, we have the second store drop along with the ejection force, and that causes our response here. So the forward swept wing closed loop system is equipped with a flutter suppression control system that's identical to that of the closed loop forward swept wing maneuver loads analysis. And the ejection scheduling of the store masses and jettison forces is the same as the open loop system. And in order to demonstrate that the ejection loads analysis can simulate the store ejection condition while the aircraft maneuvers due to a pilot input command, we will use the MLD command bulk data card to specify a pilot input command to the canard. And the outputs are specified through the MLD print bulk data card, are nearly identical to the open loop forward swept wing system. The bulk data cards are nearly identical. This is the interrelationship. So much like our previous maneuver loads analysis, we now have a closed loop control system. So we have our three sensors feeding to the MIMO SS, which implements the controller. That then feeds to our three actuators, canard, trailing edge flap 1, and trailing edge flap 2. Meanwhile, we have an external input, which is the pilot command. So that is added to the controller output to the TE flap 2 actuator. And now if we look at the response, if we look at acceleration at grid 90, we can see when we drop the store, we have the same initial response, and then we also have a larger response here, which is due to the pilot command. And then after we drop the second store, we have a second large response. And then we'll look at the wing root bending moment, comparing once again the mode displacement option and the summation of force RFA option shown here.